All right. How we doing? So I just graded, not just a couple days ago, I graded your first written homework. So those should be in. Um, Overall, I was really impressed by the level of like not only how well it seems like you understanding things, but how well you're communicating what you're doing. So keep that up. I also did I post the solution? Okay, I meant to. Okay. If it's not there, then I'll put it up, but I think I did. I wanted to. Okay. Any questions about anything about the class going before we get back into this? Okay, so a couple more things I want to talk about with partial fractions. We have not done a definite integral yet, so let's do one. So it's been 5 days. How should we get started here? Okay, I need to look at the possible denominators. In this case, what are they? Okay, I have a vote for x plus 1 and x plus 1 squared. So this is that case where I have a repeated root. So because of that, I have to account for every possible power of that root. We agree with this so far? Okay, from here, where should we go? What's that? We're gonna do a define. So, and really, we could define an x right now to start eliminating some terms. I strongly recommend taking a step before we get there. Yeah, or basically multiply both sides by the denominators, so I can clear all my fractions out. So I'm going to multiply both sides by x plus 1 squared. And then what result will that have? On the left-hand side, I have what? 2x plus 3 equals a times x plus 1 plus simply b. So all that to say, yes, you could start plugging in x's from that first step. I think it's going to be a lot more manageable here. What's a good x value to try? Y negative 1. What's that? Next, so yeah, it zeroes out the a term. So should get me b for free. So the left-hand side becomes 2 times negative 1 plus 3 equals just b. All that's left on the right-hand side will be b. So I should get the b is equal to 1, right? We agree with that? All right. Got one of my constants. How can I get the other one? Can I choose a value for x again?
Can you choose a value for x and then plug in b as well?
Yeah, so here's what we know about a and b from the start is that, yeah, we don't know what their values are, but we know that they're constant. So once we find a value, we don't have to worry about that one again. So we know that b is 1 for all values of x. It is constant. So because of that, I'm going to choose, just throw me a number. Give me your favorite number. 2 sounds good. We did 0 last time. So x equals 2. What does that give us? 2 times 2 plus 3 equals a times 3 plus b, which is 1. So 7 equals 3a plus 1, which means that a equals 2. I don't think it matters what you plugged in for x there. You're going to get, basically the only thing left is once you find a value of, or once you choose a value of x, the only unknown that's going to be left in that equation is going to be a. All right, so I have a, I have b. So what? What can I do with those things? Right, so now I've basically traded the integral we started with for this new one, which is What's a? 2 over x plus 1 plus 1 over x plus 1 squared. All right. How does that integrate? How about 2 over x plus 1? I'm hearing whispers. 2 natural log of something. The absolute value of x plus 1. Plus what? 1/3? Oh, we got to integrate both terms first. Not quite exactly 1 over x plus 1. You're very close. Should be minus 1 over x plus 1. Why is that? So off to this little box over here. Basically what we're doing is this. The integral of u to the negative 2 du is equal to negative u to the negative 1. Okay. Is that everything? Yeah, now, so let me stop there for a bit. We got the antiderivative. So we've done the indefinite part of this integral. Do we need to revisit anything? Are we happy with how we got here? If you're not, now's a good time to get some clarity. All right, so if we're good with the antiderivative, now we can plug in our limits. So I get 2 times the natural log of 2 minus 1 over 1 plus 1, so minus 1/2 minus 2 times the natural log of 1 minus 1. So any simplifying I can do here? Natural log of 2 is a irrational number, so I'll just leave it exact. What's the natural log of 1? 0, so that goes. So then I have 2 natural log of 2 minus 1/2 plus 1 plus 1/2.
Wait, why is it plus 1/2?
So I just added the constants together. So negative 1/2 minus negative 1.
Oh,
Also minus negative 1/2 plus 1. What else? Feel good about it? So basically, the first 90% of what we did here is identical to the other, 6 examples we did. But once we have that antiderivative, we want to evaluate it over our interval. I got one more for you. What do we do with this thing? This hideous function. Do we have any idea if we can factor, or is there any simplification we might be able to do?
I think it's that.
Okay. How would you like to do that?
E to the x plus 1 to the 2.
So that's what is that the denominator, I assume? So you said, let me just write down what you said. So you're saying maybe e to the 2x over e to the 2x plus 3 e to the x plus 2 is equal to, left that alone, over e to the x plus 1 times e to the x plus 2. Does that make sense? How'd you do that?
Oh. Factor it. Well, e to the x. Like if you factor it, well, no, because then it would be 2. Well, I don't know.
Okay.
Even 2x subtract 1, so there's 1 on top of it. You know what I mean?
Sorry, one more time, say that again.
The Even the two x, does it not turn into one since there's one on the numerator, one on the denominator?
We can't divide that way because you have to divide basically. You have to divide the numerator by the denominator all at once. So for example, if I have 3/3 plus 1, that is not equal to 3/3 plus 3/1.
Where like if you multiply e to the x with e to the x, would it be 2 e to the x or e to the 2x?
So that's a good question. Let's think about that. So when you multiply things together that have the same base, like these do, what do you do with their exponents? You add them, right? So e to the x times e to the x is e to the 2x. So I believe that that's okay. I'll tell you right, this thing that you came up with that you don't seem to have any faith in anymore is perfect.
Yeah, it doesn't look like it does do anything.
I disagree. I think this is fine, but here's one thing that I might suggest to make it easier to look at. So you treated the denominator of that, whether or not you realize it, like quadratic and factored it, which is fine, but let's put in kind of a helper so we don't have to look at these exponential terms until we need to again. So if we make this substitution, then what does this integral become? If u equals e to the x, what does du equal?
E to the x.
E to the x dx, right? So now let's rewrite this integral. This becomes e to the 2x is u squared over, and let's just go with the factoring we have. U squared over u plus 1 times u plus 2 times dx, which is what for us? How can I rewrite du over ex, right? We've already e to the x times du over e to the x, which can't I say du over u?
Yeah.
Okay. Does that help us at all?
Can we cancel out if they do that, we have to continue with one of the ones that on top of the use square?
Absolutely. So now I have this u over u plus 1, u plus 2. So now we're bringing in substitution to facilitate this partial fractions thing. Any questions about how that got done? Okay, so now that we're here, now we have an integral in terms of some other variable. How can we handle this integral from here?
The same way we usually do?
Yeah. So basically now we're doing partial fractions. So what should our setup look like here? So I'm trying to decompose u over u plus 1, u plus 2. What does this decompose into, just for starters? A over u plus 1 plus b over u plus 2. Do we agree with that? All right, how do we move forward from that place?
You multiply the denominator and both sides.
Okay. Clearing the fractions gives me u equals a times u plus 2 plus b times u plus 1. I like it. Can we choose some values for u that are helpful? I got to vote for -2. What will that do, Saul?
It will swap b.
It will cancel out this first term on the first term on the right hand side. So -2 equals b times -2 plus 1. That should give me that -2 equals -b. So b equals 2. What's another good u value? -1. So that gives us -1 equals just A. Okay, so I got B equals 2 and A equals -1. So now I can integrate this thing. Integrate -1 over U plus 1 plus 2 over U plus 2 with respect to U. All right, so now I got two terms. What's the integral of -1 over U plus 1? Negative natural log of absolute value of U plus 1. And the next term? Okay. All right, are we done? No, one last step, which is what? Right, so undo our first substitution. So negative natural log of e to the x plus 1 plus 2 natural log of the absolute value of e to the x plus 2 plus c. Any questions for? So did a substitution, then we ran through the partial fractions, then integrated the partial fractions once we found them. Any questions about any part of that process, why we did things? Makes perfect sense. Probably not. Okay. So moving on. So one thing that this next section is going to require is access to the textbook. Does anybody not have access to it by now? Okay, good. So the next section we're going to talk about is entitled integration by tables. So at the back of the textbook, here I'll show you. Basically, there's a long list of formulas that you have access to. What is it? Is this what the book looks like for you, or is mine a little different? Or is this totally foreign to you? Or have you just not looked at the book yet? Okay. So basically, the things you're going to need for this section are the very bottom of this, like left-hand window here, the reference pages. And then once you go inside the reference pages, I think it's page D. Let me see. Differentiation. Nope. Integrals. So reference page 6, like it starts out with all these, what it calls the basic forms. So hopefully that one looks familiar now. Hopefully that one looked familiar maybe last semester. I don't know how deep you got in antiderivatives, but a lot of these you don't really need the tables for. Like these are the ones I'm not necessarily going to give you on a test, for example, but these ones, like a lot of these, yes, I'm not going to expect you to put these ones to memory. So a lot of these are, like especially after 20, basically that's what this section is going to we're going to kind of train you to do here, is recognizing what form the integrand has and trying to find the right table to help you deal with it. So wanted to start off by showing you where all those things are, but now let's look at a few of these. It's actually a pretty short section. Can I put these side by side? Maybe I can. All right, can we see both of these? All right, good. So it's cosine x over sine squared x minus 9. We want to try to find one of these, basically one of these formulas in the tables that might help us. So let's look at the headings. So basically everything under this heading is things of the form square root of a squared plus u squared. Do you think we're going to find our answer in here? I see some head shakes. How come? We don't have square roots. So keep on going. Same reason I can leave this one behind, right? And that one. How about a plus bu? So maybe it's a good time to ask this question. What relationships we see between the terms in the thing we're actually trying to integrate? So this cosine of x over x squared plus 9. Where's my cursor? These are all starting to look less and less relevant. So let's go to the top. Maybe it was some of the ones in the top. So I don't think it's any of these like first 10 because there are no real fractions to worry about there, but maybe one of these last 4. Go ahead.
So when we're at the test, will give us the data sheet.
I'll give you a data sheet. Yeah. What about 20? Why do we think 20?
Because it has the sine squared. And then the 9. It kind of looks like the ones that we did before.
Okay.
But instead of just x, it has the cosine.
Right. So I think with the trig substitution ones, all those we those dealt with radicals, right? So we're not quite there, but so let's look at 20 again. I mean, our function does not, I mean, these tables are very general. It should work for any variable function u and for any constant a. So can we make our integrand, the thing we're trying to do, can we determine, like, can we like match them up with u and a? So what's a good u to choose for us? Sine of x, does this work? Oh, it's going to work, I think. In black, okay. U equals sine of x. If u equals sine of x, what does that mean about du? Cosine of x dx. If we rewrite this integral in terms of that u and x, what do we get? So we should get du over I think the dx got swallowed up by cosine, or with the cosine. All right, does that make us feel a little better about 20? Or did you notice that I wrote that in the notes down there?
Oh.
I might think I wasn't counting on you being able to see that, but you totally can. If I hide it from you, I hide it from me though, so I'm gonna leave it. But does that make sense with the table we like, our form and the way the table is written?
Yeah.
Cool. So now you can apply it. So what does the integral become per the table? One thing which to point out. Yeah, we can do that. Definitely. So that I was going to write down what a was, but that's probably even more logical. So this becomes du over u squared minus 3 squared. So that should make it even more clear. how all these things line up. So what does our integral become? 1/6. So for now, I'll do this. 1/2 times 3 times the natural log of the absolute value of plus c, right? And we should do one more thing to complete this. Yeah, 1/6 natural log of sine of x minus 3 over sine of x plus 3 plus c. Go ahead.
We can do like another way to solve it, or if we use that.
There must be, because like these formulas came from somewhere.
Yeah,
Looking at it,
like that we could have done.
it's not jumping out at me like what the kind of like by hand way would have been to do this. I'm sure it must be there. Since this like gives a natural log integral, there's probably a way to set this up where it's some function in the denominator, some derivative of some multiple of the derivative of that function in the numerator. I'm not seeing exactly how that looks right now, but I think even getting there would take some algebra to manipulate it. It's not there. It's not ready to do that in that form. How are we doing? Okay, go ahead.
So we're provided all of these on like a text or anything?
I'll provide you the ones you need. So like when I say the ones you need, I hope this doesn't offend you if I say I don't think you need like the first like 11. Like those are the ones I expect you to kind of bring with you. But yeah, once you get into the more obscure things, yeah, like number 20, I just said, I don't know how I would get to that integral. If I gave it to you in a test, I mean, it would take me 20 minutes to figure out how to do it by hand. I can't expect you to figure that out and do a bunch of other stuff in 50 minutes. So I will give you the ones you need. Since you're asking about a test, I'll put it to you this way. If I give you an integral and you don't think the table's on there, you might want to look for something else. I will give you the tools you need to get these things done. How we doing? All right, moving on. All right, what's going to work here? So let's look at the headings again. So the radical of a squared plus u squared. Does that make sense to look there? Yeah. No, you don't need to be sorry. You're good. That's maybe a little overkill, isn't it?
Thank you.
Yeah. Is that better for everyone?
Yeah.
Okay. All right. All right. Same question. Does this heading, so the square root of things that look like a squared plus u squared, probably not there, right? What about that one? I see some head shakes. I hear some maybes. I think it's at least worth looking at because we have. Could I represent 5 as a squared? I mean, we don't think 5 is not a square number, but its square root is real. We can at least, yeah, maybe something will jump out of here, but yeah, there's no. Just because our numbers are going to have an irrational square root doesn't mean that we can't use these formulas. So having said like this column is worth looking at, how do we feel about 30? 31? Why is 34 logical? U squared where? U squared over that radical, right? All right, so we're going to try to use 34. Do we need to figure out what our U's and A's and all that stuff are?
Yeah.
What's U? I'm going to vote for x squared being U, or just x. Okay. What's A? A should be root 5. If U is x, then du equals dx. So let's try these things. This integral should become x squared, so that's u squared, over the square root of a squared minus what? Okay, so now we're straying from the formula a little bit, right? Is that a problem? It might be. So I recommend a slight adjustment to the definitions we tried to build this on. If I heard votes for 4x and 2x. Let's fight it out. Okay. We like that? Okay. So if u is 2x, then du equals 2dx. All right, so this didn't work, but I think it's worth keeping because we can compare and contrast with what we end up with now. What does that make the numerator of x squared? If u is equal to 2x, then what is x equal to? U over 2. So this becomes u over 2 squared. Again, we're straying from the form, but maybe that's not going to bother us as much this time. Now the denominator becomes a squared minus simply u squared, right? Try to draw 2. Fourth try. Here we go. What does dx become? Times du over 2. So we're not exactly the same as the form we're trying to mimic, but is that okay? Go ahead.
How about it's in the numerator and just put it outside the integral?
In the numerator here? Not exact. It's not going to exactly be 1/2, but we can definitely pull it out. So let me do some simplifying. I believe the numerator you're going to have u squared over 4 over radical a squared minus u squared. Would you be offended if I pulled this half out like that? And then we also had a vote to pull the 1/4 out, right? So I believe this becomes 1/8 times the integral of u squared over radical a squared minus u squared du. Are we happy with that? Does that mimic the table? Okay, so that should be good. So based on the table now, so 34 was good. This integral becomes what? 1/8 times what? Minus u over 2.
A squared over 2.
Times the inverse sign of u over a plus c. This one I have a lot less confidence about where any of this comes from. Okay, so now we're going to start dropping our values in. What is u?
Right.
So 1/8 times negative 2x over 2 times the square root of 5 minus 4x squared plus 5/2 inverse sine of negative, no, not negative. 2x over radical 5. Obvious, right? So that's why these tables exist. I'm not sure how I get there by hand. So, any questions about the manipulations we did? How we decided this table was the one that was going to help us how to find these things. If I'm not there to find them for you.
Do you want them to be an exact match, even like without the constants or the coefficients next to them?
I think it'd be best because let's go back to the one I crossed out. Like, I'm not saying you can't do it from that step. I think it becomes. I think it'd just be hard to keep track of the modifications that you have to make on the fly, as opposed to, you know, when we went with the form that we actually went with, all the things that made us different from the formula were constants we could remove. That 4 next to the u squared in the radical, you can't. We're kind of stuck with that one. So it's about I think it's a question of making the manipulations that are going to be possible to make. Good question though. Go ahead.
So unless it's on a test where we only have like a set amount of the table.
Yeah.
Does it work to use the table for the ones we were doing like the trig substitution for?
Yeah, that should be fine. I don't. So again, this is a coordinated class. I don't think those are going to be on. I don't think those ones are going to be given to you. I don't think. But like these ones, I can guarantee will be there, or I can't guarantee anything. I can almost guarantee that. There's no reason for us to expect you to have any of these committed to memory. What else? Okay. Moving on. So let's go back to the top. So outside of the ones that are calling basic, which not all of them are super basic. How about this section? Things involving the radical a squared plus u squared. Does it seem like we're going to find what we need in there? What was that? Maybe. So this one, I'll tell you, we are going to use Rule 21. It's probably deeply not obvious that that is the one that we're going to lean on, but that's the one we're going to use. So I'm going to bring back something that you probably haven't done in a while, and that's completing the square. Is that something we've heard of? Okay, I think I heard a small groan, so that sounds like it was familiar. So does anyone remember how to do it? Okay, so completing the square is the thing you do on quadratics. So basically, I want to take a quadratic, the one that looks like x squared plus 2x plus 4, and I want to make it look like something squared. So x plus something squared, and I might have some constant left over. Go ahead.
Whenever we want to make x squared plus 2x plus 1, so we do minus, I can split the 4 into 1 and minus 2. I mean, no, I mean 1 and plus 3.
How'd you get the 1?
There's a x plus. Because x plus 1 squared is x squared plus 2x plus 1, right?
We agree with that? So first thing I'm going to do is rewrite this as x squared plus 2x plus 1 plus 3. So the reason like I'm really leaning on the phrase completing the square is because the process that you were probably taught is very long. And if you want to go through that, if you want to remind you how that works, we can do it. But the real purpose of completing the square is to get your quadratic to contain like this square binomial that looks like x plus a squared. Which, if we break the 4 down into 1 plus 3, I think we can see that. But that was kind of a shortcut, and it only really works if you recognize how the x squared and a 2x, like what number is going to complete that square. So first of all, do we recognize that x squared plus 2x plus 1 is a squared binomial? Do we want to see like the long form completing the square thing again, or is that? What if I do it quickly? I feel like you at least need a reminder. So I'm trying to complete the square on x squared plus 2x plus 4. First thing I'm going to do is write down a few numbers. So what's the coefficient of x? That's 2. What's the half of that? That's 1. If I square that, I get 1, right? So basically this is b, this is b, and then b over 2, and then b over 2 squared. So basically this number 1 right there is the one that completes the square. So because of that, probably what you've seen done is, okay, I'm going to add the 1 to the x squared plus 2x plus 1. But the only way to do that legally is if I balance that out on the opposite side or outside the parentheses. So all that is going to get us to the same place that we are now, which is equal to x plus 1 squared plus 3. So if I rewrite this integral as the integral of x times the square root of x plus 1 squared plus 3 dx. Is it any clearer that rule 21 is the one to use?
It's not x outside of the square root.
Yeah,
It's
it should be. I'm starting to wonder if I had a typo in here. So let me see if I can find the one that's going to make sense. Otherwise, I'm going to call it a typo and edit it on the fly. So u would be x plus 1, right? Which means du would be dx. Okay, I'm going to go ahead and make an edit because I'm pretty sure there was no x on the outside here. All right, now does this mimic the rule 21? Okay. Rule 21 is all about u's and a's though, so we should figure those out. What is u? X plus 1. What's the corresponding du? Dx. What's a? Square root of 3. And that's one thing that is subtle to be careful of, is that your constant is not equal to a squared. I'm sorry, your constant's not equal to a, it's equal to a squared. All right, so based on rule 21, what should this integral become?
over 2 plus square root of a squared plus b squared.
That's a squared over 2 times the natural log of u plus radical a squared plus u squared plus c, right? Now let's drop into things we know. X plus 1 over 2 times 3 plus x plus 1 squared plus 3/2 natural log of x plus 1 plus radical, not a, 3 plus u squared, x plus 1 squared plus c. I'll have more room. How we doing? Let's see some sad faces. We're good though? All right. Any questions about how we got to even recognize that that was that rule in the table? So these tables are not exhaustive. Trying to basically, there is going to be some work on your shoulders to make some manipulations algebraically to get to the place where the table can handle.
If you have a polynomial under the square root bar, when you see it, should you always just try to complete the square or factor it?
Not any polynomial, but a quadratic, absolutely. So you can always square, you can always complete the square on a quadratic. One thing I want to point out here is the way you complete the square on a quadratic has nothing to do with that 4. It's all about the x squared. So yeah, x squared plus 20x. Like you could easily, or not easily, you could find the number that completes that square. So no matter what those numbers are. All right, last one. Do we have time for it? Okay, so again, sticking with we got 3 minutes, so let's at least see if we can't find the right tool. Forms involving radical a squared plus u squared. No? I would think not. This is about a difference. Is it inside these ones, radical a squared minus u squared?
Yeah.
I would rather have the variable first. So, I mean, and part of this is knowing what the categories are. This is a lot closer to the thing we were just looking at because we have a difference, but the difference you want is the one that has the variable positive and the constant negative. What's that? Are you sure about 42?
Yeah. Yeah.
So 42 looks close. So let's at least do this. Let's try to set up the substitutions that are going to help us get there. What's our u? I got to vote for 2y, which would make du equal to 2 dy. What's our a? Root 3, right? Okay, so let's try to modify this. This becomes the square root of what? I don't think that is u squared. Because u squared would be what? 4y squared. So let's try u equals root 2y. All right, going that way. Now what's under the radical? U squared minus a squared, right? Over what? If u equals 2y, or radical 2y, then what does y equal? U over root 2. So this becomes u over root 2 squared. What's dy? Du over 2?
But wouldn't we have to change it? If it changed you?
One of them.
That's what I was doing. I'm sorry.
Oh.
So the dy, yeah, we got to transform the dy. So I have du equals 2 dy, right? Does that mean the dy equals du over 2? Thank you. Oh, yeah. Well, that's what you're yelling at me about. Yeah, I deserve that. So that should be fine, right? First try. So I'm at time. I'm going to ask you for 20 more seconds so I can really show you that this is going to work. So this is u squared minus a squared over u over 2 times du over radical 2. Yeah, you're right. That's the whole point. What's radical 2 over 2? That's 1 over radical 2. So I think if I pull that out, I'm going to get radical 2. All right, so we're going to stop there, but I think the real important part about these is making sure you can make your integrand look like the thing in the tables. And then from there, it's a matter of translating the thing you had or translating the table into what works for you. How are we doing? All right, reminder, I got office hours upstairs in half an hour. Otherwise, I'll see you Friday. I'll pause. Stop.